Okay, I will start the recording here.
Let me. Okay.
Okay, Jesus.
Okay.
Go ahead.
Good morning and good evening to our guest. Thank you for attending the Bolivian Symposium Mechatronics, organized by Scientific Student Society of Mechatronics Engineering. It's a great pleasure for us to introduce our first speaker today, Yegor Piskarev, who is going to talk to us about his experiences as robotics and mechanical engineering. Before starting as doctoral assistant at Laboratory of Intelligent Systems at EPFL, Igor got his master's degree, mechanical engineering at EPFL. While there, he worked as research assistant and participated in different conferences, such as International Conference on Intelligent Robots and Systems, with his study on soft robotics. So now I am delighted to hand over to Yegor Piskarev, who can tell us more about the exciting work he's doing on soft robotics and at EPFL. So over to you, Yegor.
Okay, awesome. Jose, thanks a lot. Thank you for the invitation. First of all, guys, can you hear me well?
Yes.
Okay,
yeah,
gotcha.
Everything
gotcha.
okay.
Let me first of all share my screen with you. Unfortunately, I can't do that right now. May I somehow share my screen? Because for now, this function is unavailable. Just can't do it.
Oh. Let us check.
Yeah, sure. Absolutely.
Job, could you verify or give permission to Yegor? Okay.
I'm doing that.
Start video, make host. Now, Yegor, could you
let me check it out? I can't.
Okay.
The demonstration for the participants is turned off. That's what I've got. So yeah, I can't.
Let me. So, the spotlight, my host, cool. Host. And now, could you?
Absolutely, I can.
Okay.
Yeah, let me just do that. Okay, guys. So, what can you see now? Can you see my slide now?
Yes, we can see your slides.
Okay, so you just see the slide, right?
The slides?
Yeah. No, it's okay.
Okay, great, awesome. In this case, let me start. First of all, thank you all guys for coming. I really appreciate it. I'm super excited giving this talk to you guys today. I also would like to thank Jose, my friend and the collaborator. I hope at some point for inviting me to this event. It's a pleasure for me to presenting in front of you guys. So well, I will just start. Dive into the outline what I'm going to show you today. So first of all, I would just start with the background of myself, who am I and what I'm doing currently right now. Then I would just briefly mention what we are working on right now in our lab at LIS at EPFL. After that, I would try to briefly talk to you guys why soft robotics is cool. Because probably for most of you, soft robotics is some kind of a new subfield of robotics, and I would like to give you a high-level overview of the context, the motivation, why we're working on this field and what we're trying to achieve there. Finally, I would like to talk with you a little bit about the difference in the research approach between the academia and the industry, because most of you guys, I suppose, are the undergrad or graduate students at an engineering school, right? And an engineering school, usually the approaches are a little bit different from the fundamental or academic approaches. And that's something that I'm going to try to show you through my projects. Some of the projects actually that I accomplished being a master's student during my master's program. So also that would give you guys some kind of a rough idea of what are the projects our students are working on nowadays at EPFL. Okay, so I'll just start with my background. Actually, I got my bachelor degree in Russia, in Moscow, in Bauman Moscow State Technical University, in the Department of Mobile Robotics and Automation. That's actually the same spot where Jose's been studying, and that's actually how we got to know each other through these brilliant people. These are our former advisors in Russia. I appreciate them a lot through all my, for actually all my achievements throughout my bachelor. And actually also due to my collaboration with them, I got to come to this beautiful place called EPFL, École Polytechnique Fédérale de Lausanne, that is located in Lausanne. That's a town on the shore of Genic Lake, located actually, yeah, as you see here, right here, in the middle of the Genève Lake, and that's the view that you see. That's a Genève Lake, and these mountains are Alps, and actually that's France already, right? And we're right here in Switzerland right now. And currently, I'm right here at our EPFL campus that is located right on the shore of the Genève Lake. And what you see here, that's our beautiful library. And actually, this building called Mechanical Engineering Building. And I am actually right now talking to you guys right from this window. That's my office, located right here in this fancy building made out of glass and steel. So this university is quite new. We've got around 15K of students right now, and the world ranking is usually between 14th to 18th. It's fluctuating every year. Now we're on the 14th spot, but of course we would do our best to climb higher. Okay. So actually, what I just came to EPFL in 2016 to start my master's degree here in mechanical engineering. I did a few semesters projects with this brilliant scientist. His name is Jun Shintake. Now he's a professor at Tokyo. In Tokyo, he's doing soft robotics, and actually under him, I was working on a few projects. I was working on the edible grippers, edible soft pneumatic grippers and actuators, and also soft sensors. And that's actually how I got to know what is soft robotics and what are the challenges in this field, what is exciting parts about it. And I would definitely talk more in details about these projects, okay? Probably more like in the second part of my talk today, okay? So that's how I got through this project. Then I actually finished my 4 semesters at EPFL, and as a final part, I went to the US, to NC State, that is located right here in North Carolina, actually in the city called Raleigh. Raleigh is the capital of North Carolina. Probably people are more familiar with other city called Charlotte, because it's just larger. And also, if you guys are keeping track of NBA, Charlotte Hornets are from this city. However, in Raleigh, we also have an NHL team, Carolina Hurricanes, that performed not that bad actually last 2 seasons. And that's also a beautiful, magnificent city. And that's actually how the campus there look like. We've got also just unbelievably great library there. It looks super fancy, super nice, calm, large campus there. And actually there at NC State, I was working with Michael Dickey in the Department of Chemical and Biomolecular Engineering. Seems to be, at least from the name, absolutely far from robotics and from my background in mobile robotics and mechanical engineering. However, guys, I would tell you that it's not that far, actually. It's not that far. And Michael is just a brilliant scientist. He has been identified as one of the most influential researchers in the world this year. It means that he's in top 0.1% in 2021 research fields right now. Talented, but what is more important, that he's extremely nice person to communicate with, to work with, to spend time with. And there I've been working on the variable stiffness actuators using liquid metal. Why liquid metal? That's of course because of the focus of Dickey group, because Michael is working a lot with liquid metals, and actually his ultimate goal is, if you saw Terminator 2, in Terminator 2 there was a robot, his name is T-1000, that's a robot made out of liquid metal, and that's actually something that Michael would like to build in the end of his path. Of course, it's probably a little bit, we're a little bit far from that right now, but I mean, that's a great ultimate goal, I would say. So yeah, and actually during this time there in the US, I tried to combine my expertise that I've got at EPFL in soft actuators and soft sensors together with his expertise in liquid metals to get something novel out of it, but that was these variable stiffness actuators, okay? And then after that, I came back to EPFL and started my Ph.D. there in the Laboratory of Intelligent Systems under Dario Floriana. So he's well known for his works in AI, drones, and soft robotics. So you can read more about him on the Wikipedia page, for example, because he's an extremely well-known scientist. And in his lab, but I'm right now, currently, I just doing my third year of my PhD there right now, so I hope to finish next year. Well, yeah, we'll see. I'm focusing on the topic called tubular variable stiffness technologies for different applications. So as you can see here on this picture in the middle, that's a smart fiber that has different capabilities, potentially different sensing capabilities. We can sense humidity, temperature, any other thing through it. It potentially can actuate, would change its state from rigid to soft, from soft to rigid, and then could be potentially woven, for example, in the clothes, or can be used with different robots, or also in medical purposes. And that's kind of my ultimate goal. So ideally, I would love to develop such type of a versatile thread that could be easily applied in different domains in order to build some new capabilities, right? So yeah, that's kind of my vision that I'm following right now. And now I would like to move on a little bit on what we are working on at LIS, because our lab is extremely diverse. We are working on a lot of different things. For example, we're working on soft robotics, aerial robotics, and machine learning. So these are three main subdomains that we're focusing on right now, okay? So in the soft robotics, as I mentioned before, I'm working on smart filiform tubular structures that could be potentially applied, for example, in medical robotics. So that's a paper that you see on the left-hand side. That's from my very recent paper. It's not submitted yet. It's under revision. That's why I'm not able to show you my results. So yeah, hope to share these results with you guys next time. But yeah, that's just trying kind of to give you an idea of what we're focusing on here, okay? So then the integrity structures that you see in the middle part, these are the structures that are composed of and rigid bars. As you see here, these are the struts and these are the rigid bars. And these structures are extremely lightweight and have a really great strength to weight ratio. That's actually because these structures are always under the tension caused by the tension of the struts between these rigid bars. And we can build quite a lot of different things with different scales and shapes out of these structures, starting from the fuselages, the bodies of drones, as you see here, up to actually buildings. Yeah. And then actually what you see here on the right, that's a really fancy new field, absolutely new field called edible robotics. I will talk about it a little bit more in details here. So what you see here, edible robotics, it's kind of an interdisciplinary research where robotics meets food material science. And these edible robots why they attract such a lot of interest in the last years, just because the edible robots can be used for different interesting applications, different interesting purposes. For example, we can use it to deliver different life-saving nutritions to people that are in emergency or that got lost. See, and yeah, actually we also put our milestone here with the soft pneumatic gelatin actuator. That was actually the first edible actuator. For now, I would also like to a little bit focus more on the application part. So what we've been talking before, they're more like technologies, right, or subfields. But what are the things that are actually building? What are the final devices, right? So what you see here on the top left, that's an exoskeleton. You see the structure, how actually it looks like here on this picture. What we can do with this exoskeleton, by changing the posture of your body, we can control the position of the drone, and we can actually use it to control the drone during the flight. Now this project is finished actually. So then what you see here in the bottom, it's a versatile soft gripper. That's an extremely interesting project. I will talk about it in a few next slide also. But what we have tried to do here, the researchers at LIS, they tried to develop a gripper that combines the electric elastomer actuators together with the electroadhesion in order to be able to grasp, first of all, fragile objects, then highly deformable objects that you see here, these balloon made out of silicone and filled with water, and also flat objects. So for the soft grippers, that is extremely challenging to be capable of lifting such a large variety of different objects. I will tell a little bit more in details how guys achieve that. Okay. Then edible actuators that you see here. This is actually a soft pneumatic actuators, but made out of edible materials. And by combining two actuators together, we can get a gripper that could be used to grasp different objects. And due to the fact that it's edible, meaning that it's biodegradable, then it can be, for example, dissolved. Then catheters. So in my research, particularly together with ETH Zurich, I'm focusing on new generation of catheters, or new, actually that's a new generation, new approaches to build catheters for cardiac ablation surgeries. It's quite challenging because the diameter of this catheter is usually 2.3 millimeters, and in this structure we should be able of having different capabilities, variable stiffness capabilities, sometimes heating systems, cooling systems, sensors, and also working channel to provide, for example, a cooling to the tip of the catheter. So now I would like to focus a little bit more on this gripper, because that's a extremely interesting development in my opinion. So what you see here, that's a gripper that composed of two actuators on the right and on the left, that is capable of lifting deformable objects, fragile objects as this raw chicken egg, and flat objects as this sheet of paper. Okay, what is the structure behind it? So actually that's a layer by layer structure where we have a two passive layer made out of silicone with a thickness of 100 micron. Inside we have two electrode layers made out of conductive silicone. Usually to make silicone conductive, we just mix together the conductive particles with the silicone, and then a blade cast it onto the silicone layers, and then these layers put it in an oven can be uncured on each other. And then a pre-stretch layer, a dielectric layer. So what you have in the end, in the middle, that's a sandwich structure where you have two electrodes and the dielectric layer in between them. So that's basically a capacitor. And when we are applying high voltage to both compliant electrodes, these compliant electrodes would try to squeeze the dielectric layer that is in between them due to the Maxwell pressure that occurs between them. And due to that, we would be able to change the bending angle of the actuator from bending state from bend state to straight state. Why we can do that? Because when we're squeezing this elastomeric layer that is in between electrodes, we're changing the height of this layer. But due to the fact that polymers are incompressible, meaning that the volume is always the same, this polymer would expand in these two dimensions, right? Causing it to be straight after. So, but that's just about the electric elastomer actuators and how they work. But what about the electroadhesion? These tiny interdigitated electrode structures that you have here on both ends. So what is the idea here, that due to the fact that you have this interdigitated electrode structure, you have also Fringle fields that going out of the electrode structure and out of the top passive layers that you have on top. You can clearly see this figure here. And if we will just put, for example, a sheet of paper onto this silicone sheet, this paper sheet would just stick onto the gripper due to the electrostatic attraction, meaning that in this case we can not only bend and like grasp this object from both sides, but we can also, on command, stick onto this surface. And that's just a and that's just a short video to give you an understanding of how this actuator, how this gripper composed of two actuators works. We apply high voltage. Now we're able to lift this egg. What is really interesting about these actuators, that these actuators are extremely lightweight. So the weight of them is just a few grams, and they are able, they are capable of lifting the objects with the weight of 1,000 times heavier than the weight of the gripper itself. And these are actually Herb Shi and Dario Floriana who developed this this gripper. Yeah, okay, let's move on. So that's about the first subfield in our lab. Then we're also working a lot on the aerial robotics. In the aerial robotics, we're mostly focusing on avian-inspired drones and multimodal drones. I will just give you a little bit more project example that we have here. We have this Rapture-inspired drone that can move and actually change the area of its wings and the tail. I will talk about it a little bit more in details on the next slide. Then we're working a lot on the aerial swarms in complex environment, this video that you see here on the left. So we actually working on different biologically inspired aerial swarms. So birds and other animals, they show perfectly synchronized and coordinated flight. They can collectively migrate, for example, to a certain destination while staying cohesive and avoiding the collisions. And what we want to reproduce, that's actually this type of collective behaviors with flying drones. In this case, they would potentially be able to integrate in our environment safely. And if we would like to achieve it, of course, the level of agility and obstacle avoidance, these are the fundamental skills that we would like to achieve in this research domain. Okay. Then what you see here in the middle, that's a delivery drones that are covered with some kind of a protective mesh here. These drones actually now, that's a startup at EPFL. They're trying to attract some investments, I think. And what these drones are capable of doing, they can be used, for example, to deliver medical things or different pellets in cluttered environments. Okay. Then we're also working on the different perching strategies. So this is what you see here. That's an approach of perching with the recuperation energy. So what you have here, on the face of the drone, there is a claw, and what this claw can do inside, we have a bistable mechanism, and when this claw is actually crushing right onto the rod, we don't need to decrease the speed of the vehicle. We don't need to think about the control strategy. We just need to crash onto the road with a certain speed, and some of the energy would be stored in the springs that we have inside this claw and in this bistable mechanism here. And then we can use this energy to open the claw. So actually that's our approach to recuperate the energy during the purging, okay? And then we are also working a lot of different insect-inspired drones. What you see here, that's the drone. Yeah, you can probably see it here on the video. Yeah, that can what it's actually doing, it has these two ailerons as different bugs. And if it's in an upside down position, it can use it actually to put its body back. And that you see an example from the nature that got expired by. You see, so actually insects are doing exactly the same. And that's something that we're trying to achieve here. Okay, so this just kind of to give you an overview, an idea of the current project that we're working on. So here, that's I would like to stop a little bit more on this project because it's actually super exciting. It was published in Science Robotics last year, made by my friend Enrico. So what is an idea here that birds are absolutely amazing creatures, right? If you will take a look at the birds, they are able of changing the area of their wings in order to first be efficient during the gliding or during their way on long distances, and at the same moment they could open them in order to be more agile and be able to fly through the buildings or through the cluttered environment. And they do also the same thing with their tail. And that's actually something that we have tried to do here with this drone. By extending the wings and the tail, we can change the aerodynamic performance of the drone and use it more effectively, rather during the gliding process, or when we would like to do something more aggressive between the buildings, for example. Yep. So, and then the last part we're working on is the machine learning. So on the machine learning now, mostly we're focusing on vision-based control, either of aerial swarms or winged drones. I personally don't know much about it because it's absolutely not my part of my expertise. I would just like to give you that an idea that we have these projects. If you're interested more in that, please take a look a little bit into in the paper that I put here as a references. Probably if you'll find it interesting, yeah, feel free to contact their authors. They would be happy to discuss. Okay. So yeah, that was the next part. I mean, I finished it. So now we're moving to the soft robotics. So in this part, I would like to talk about a few things. So first, I would like to talk about the soft robotics in general. Why this concept is interesting and why, what do we mean by them? And then a really good question in anything that we're working on as a researchers is who cares actually? Who cares about the soft robotics and who can be potentially interested in the devices that we're developing nowadays or in the future. And finally, I would like to give you a few examples where we are right now, based on my previous researchers. Okay, so actually, this part is mostly inspired by these pioneers: George Whiteside, Connor Walsh, Wood. These are professors at Harvard. Carmel Majidi, professor at CMU, Carnegie Mellon University. So yeah, here we go. And actually, at the start, I would like to talk a little bit about the competition, and I would like to place this medal or like coin as a symbol of what people were always competing for, right? The people were always competing for not even people, let's be more general, like countries were always competing for money, for different resources, for gold, and finally for weapons or different sizes of the army that they have, all things like that. So that actually something about the rivalry before, right? And what we actually have now, because the world is changing, and right now actually the main focus in achieving any power or money is actually you guys, students. So high quality educated people that are capable of solving complicated tasks and doing really complicated job. And is it like a competition now for what? Of course, that's for jobs, right? And what we see now, first of all, that there is always this trade. There was always actually this dilemma between the high and low paid labor. But as you see now, actually, it's also changing, right, through the time. For example, Chinese employees now become more expensive, and European are less expensive than before. Highly and low educated people, as you see now, we are all guys can get a really good education just by moving to different countries, and I mean get the same education level as people in the, for example, Europe or US, right? So that's also something that's slightly changing. But what is more interesting in the future would be the behavior between people and robots. How would we work with them, collaborate with them? Would it be more the behavior of people with or without robots? Would robots work, let's say, independently of us, or that would be some processes when we collaborate with them? And what you already know probably, just some obvious facts, that the number of people is growing every year, right? The middle class in developed countries is beginning to disappear. Different positions like clerks, secretaries, production workers, all these jobs actually are disappearing now. And only the position requiring high skills or low paid work remains, because the robots come to replace them, right? And as you know, robots are replacing us in different segments, right? For example, as you see here on the right side, it's a factory, and these are the manipulators that are doing soldering of the cars instead of workers. Yeah, and that's great because they can do it quite precise and fast, probably faster than humans. But what I would like you guys to take a look at, actually, this old video from Boston Dynamics. And Boston Dynamics is absolutely amazing company. They're doing, these guys are pioneers in robotics all the globe. They are doing absolutely brilliant stuff. But what you see here, that's a robot that are just throwing away kind of stones, right? Structures, building structures, building blocks, and I would say that that's absolutely great that we already can build this robot that can do this. But let's imagine that some of us is staying there, right, on this spot here. Would this robot determine that we are there, and that it would be better to probably not shoot this block right now into us? This old version would definitely not be capable of detecting us there, right? Because there's just no sensors in this system that could detect it. And that's why we call these types of robots non-cooperative robots, right? Or take a look at these manipulators. You see all these measures around this. These manipulators are kind of in a jail now. That's actually not the jail of these manipulators. That's just a zone that is bounded from all the sides from the people, so that people are not able to enter it Otherwise, these manipulators through the movement can just kill the person or hurt the person, right? Of course, now there are new generations of robots. For example, KUKA are working on them when the manipulators are able to achieve the movement and the motion or the force applied onto them. But on the other hand, I think you would agree with me that it would cost much more, right? I mean, to buy this new generation of manipulators rather than just having these manipulators, old version manipulators. And I, as let's say a factory director, probably would go for this solution because it's just less expensive, right? And then just put these boundaries for all the sites. So yeah, what I want to say to you guys that these robots are non-cooperative because they're not that good in the working with people together. Not only because they don't have sensors to work with them, to detect them, but also because their nature is rigid body. I don't know, can you see my slide now?
No, I don't know what happened, but
Uh-huh.
we cannot see your screen.
Yeah, let me show
you. Will you restart your, okay.
Yeah,
could you see it now?
Yeah, yeah.
Now, yes.
Okay, awesome. Sure. Okay, let me continue. So, yeah, that's the first point. The first point that these guys are just not well equipped in terms of the sensors, right, to detect us. But the second part that is a fundamental problem, that is something inside their nature that they made out of rigid components. So if, for example, I would just try to go through one of these manipulators, it would hurt me just because it's rigid, right? And if, for example, I would at some point have the same kind of an impact with a human, I won't hurt that much because we as humans are much more softer than these manipulators, right? And then, just to give you an idea, what is the perfect cooperative robot, in my opinion? That this guy, I don't know, have you seen it? I think there is a movie called City of Heroes, something like that. And this guy, his name is Baymax. And as you see, this guy is absolutely soft. So it's actually a ultimate goal of soft robotics, being to be able to develop such type of a robot. But the reasons why make these robots soft, there are, in my opinion, a few different reasons for that. First of all, these robots are much more safe, right? If we would just, for some reason, knock into them, we would probably not even feel it, right? They are also flexible, and I will show you in a few next slide that this flexibility sometimes could also lead to their like more adaptive behaviors, meaning that, for example, if robot is rigid, you're not probably able to put it in your office. But if this robot is soft, you can try to push it a little bit, decrease the volume of it, and it will stay in this place. It's just a rough example for you guys. But the problem here is that what we would like to do, we would like to go more on this chart when you have deformation and stiffness of the material, more to the right, having something closer to biological tissue, something closer to us, to the mechanical properties of the human body. But all the actuators and electronics, batteries, quite a lot of sensors now are made out of stiff materials. And that's actually something that we would like to overcome in soft robotics by, first of all, developing these soft sensors, soft actuators, skeletons, in order to be able then in the future build more advanced robots as Baymax out of these components. And Carmel Majidi, it's a brilliant professor from Carnegie Mellon University, formed like the idea of mechanical impedance mismatch. What does it mean? So actually what you see here, these are what you see here, actually different materials and their mechanical properties in pascals. And the principle that he built is that to preserve the natural mechanics of the human body, wearable and implantable technologies must match the elastic compliance of natural skin, tissue, and organs. Meaning that if you would like to build something that you would like to put as a wearable device on your, for example, hand, as you see here, this smart glove, the mechanical characteristics of the material that you need to use in order to do not feel these objects on your skin should be in the same range as the mechanical properties of your human tissue, right? And what you see here, we as humans are somewhere here, 10 to the 5, 10 to the 6. That's where our skin is actually. And ideally for this purpose, that's the reason why in soft robotics we're widely using soft silicone elastomers like EcoFlex 030, Dragon Skin, or something a little bit more harder than PDMS, Silgard 184, Silgard 186. And now I would like to say just a few words about the inspiration. Where does inspiration come from? That's actually the story told by Professor George Whiteside at Harvard. If I can just briefly tell it to you. So once I think US Army passed by him and tell him, look, listen, we would like to have some kind of a recognizable thing that looks like a can of Coca-Cola can, but that can on command disassemble, do some job, army job, for example, surveillance, right? So to spy for somebody, probably move somewhere, spy, and then assemble back and look as the Coca-Cola can. So I would say that the application itself, spying robot, quite often for academia people is not that interesting. However, the idea, the principle that you have a reconfigurable structure that can assemble, disassemble on command and do some things is absolutely extremely interesting thing. But you know, in order to build it first, what you need to do, you need to always have a model, something that probably you would see or you would find in nature. And Professor Whiteside found this model that is actually Octopus. What is really great about Octopus, as you would see from this video, that is able to sneak through the holes that have only 10% of its own size. And that's absolutely great about octopuses. And in the end, what the Whiteside's group did, they published this paper on a soft gripper based on pneumatic actuator. So first of all, I would just show you the working principle, and then I would, first of all, I would just show you the video, what we can do with this gripper and how it looks like, and then we'll discuss a little bit the working principle behind it, which is absolutely simple. Yeah, so as you see here, by applying pressure or inflating an air into the soft chambers, we can bend this gripper and grasp fragile object as this egg. Okay, so now a little bit about the working principle. So what you have there is just, I will just show you the same gripper and how it actually performs. We have just two layers. So one layer in blue, it's a silicone cavity, silicone rectangular bulk material with a cavity inside, and this cavity is used then to inflate air into it. The second layer is an inextensible layer. You can use any inextensible material as you want. That could be, for example, PET sheet, even sheet of paper, anything. And if you would then try to inflate an air into this blue cavity, this cavity would try to expand. However, due to the fact that you have this inextensible layer in the bottom, this actuator will bend this way. And that's actually how we build all the motions with soft pneumatic actuators. We always have this structure when you have inextensible and extensible layers together. So now how to actually build it? That's relatively simple. First of all, we need to 3D print, for example, or laser cut a few molds. These are molds for the upper part and the bottom part. Upper part is this blue region here, and the bottom part is actually this green region. Then we just pour a silicone into this mold. Of course, before that, usually when we're buying silicone, comes in 2 different bottles. One is a silicone, the second one is cross-linker. Then we mix them together in the planetary mixer. After that, we degas all the air out of the silicone, and then we pour it into the mold. And what you see here is just a layer of silicone that we built together with an inextensible layer. So this red one line here with dotted line, dashed line, it's actually the green one that you see here. That's exactly the same. After that, what we do, we just stick them together with a silpoxy, that's a silicone glue. And then we just put it in an oven. And that's how we get these actuator from the fabrication point of view. Relatively simple. So after that, they went a little bit further and they did these crawling robot that composed of 5 different chambers that could be on command inflated or disinflated independently. And out of that, we can generate some kind of the crawling motion, as you see here. So this is an example of a bio-inspired robotics inspired by octopus. And as you see here, this is a quite old video. It's like 10 years old. And just to give you an idea where we are right now, 10 years after, please take a look at this video that you see here. So that's why it's interesting to compare them together, because that's also bio-inspired robot inspired by tentacles of octopuses. And as you see here, that's also a gripper. And what we can do here also with pneumatic, we can grasp different objects like drill pit container, for example, here. But this actuator is much more complicated, and you will see it in a sec. So you see the weight of this object is already 120 grams. Yeah, hammer is 300 grams. I will just move on to the most interesting part. Yeah. So first of all, let's check out what we have here. We have a kettle with the weight of 600 grams. Then, now we have also some indicators, heating and cooling. What does it mean? So inside this gripper is not just a gripper that is able to bend. This gripper can also change its state, as well as, for example, our muscles. Let's imagine that you guys are trying to lift this pen, right? Probably your muscles would be still quite soft. However, if you would try to lift an extremely heavy bags from the shop, your muscles would become stiff as a rock. Of course, if you're doing enough sports and going to the gym, right? But anyway, you would see the stiffness change of your muscles. They would become more rigid, right? And that's exactly the same capability that was implemented here in these actuator. Inside this actuator, there is a layer that has a variable stiffness capability. It can be, for example, shape memory polymer, or thermoplastic polymer, or liquid metal that at a room temperature is rigid. However, if we heat it up a little bit, it would become much more soft, meaning that the Young's modulus would change significantly under different temperatures. What these guys are doing here, they are heating on this variable stiffness layer inside. And now we're in a soft state. So the gripper is extremely soft. And now we can bend it. As you see, we would be able to bend it now. Like that. And after that, we will cool down. You see, heating is off. We're cooling down this layer. When we're cooling down this material, it becomes much more rigid. that could be even orders of magnitude if it's liquid metal. In case of shape memory polymers, probably 10 times, 20 times. And now we're able, we can lift this very heavy object due to this capability. So now a little bit about how it looks like inside. What you have inside, it's a core actuator that's a pneumatic actuating system. Then we have this variable stiffness layer, this variable stiffness filiform tube made out of polymer, and inside it there is a copper wire. So we just apply a heat, we just plug this copper wire to the power supply. We heat it up with a certain power, and due to the indirect Joule heating, this copper wire is going to heat the variable stiffness material, shape memory material, or like polymeric material that we have around. And then here we also have a soft contact sensor layer made out of liquid metal, but I'm not going to stop on it. If you would like to read this paper, it's absolutely brilliant one, go for it. Okay. So yeah, I just finished a little bit with the soft robotics overview, what we're working on there. So now I would like to give you first the idea of some of my activities that I did during my master's. And what is my goal here in this part would be probably I would try to show you the whole way that we did in one of the projects, how this project was developed at start, how we usually start the academic projects, and what the difference between the questions that we ask at the start of the project when we're doing an academia project in the academia, and you would see that it's absolutely different from the industry. And also, I would try in the end to link the moment when the industry is getting more and more interested in what we did as researchers. And you will probably try to understand this way from what we started, where we finished, and when was the moment when industry got some interested in actually what we developed. Okay. Yeah, I don't know how much time we have. Could you remind me about the duration of the lecture? Is it 1.5 hours or is it less than 1.5 hours? Because I still have quite a lot of slides to go.
Okay, we have 40-minute remaining.
Okay, great. In this case, we can do everything. Yeah, no worries. So yeah, first of all, I would start with the project on the edible soft pneumatic actuators, and I would like to start with the thing that we usually do right at the start of any research, because any good research usually begins with the good question. We call this question also research question, and I will just give you an example. What was the kind of a discussion line here in this project. Okay, so first of all, I think all of you guys would agree with me that we are building usually robots based on the live organisms, right? And what we're usually doing, we're taking the function of the live organism, like for example a cow. For example, if you would like to, I don't know, use any types of animals, like for example cow or a bull, to help you out in your dorm, for example to clean something, right, or to move something, you can use this cow as a kind of a machine, right, to move stuff in your dorm, for example. And actually what we're doing, actually then we're building machines, for example literally automobiles, cars, to do the same for us, or for example horses, right? We use them to go from one destination to another one, right? And then we build cars, but we actually kind of moved the functionality of the horses to the cars, right? And they are actually doing the same job, but much better than animals, right? And as you know, some animals, they have multiple functionalities. For example, cows or horses, we can not only use them for domestic uses, but we can also use them as a food, right? So we can eat them at some point. Not all of us, some of us don't like it, don't go for it, but some of us do, right? So why not to give more than one functionality or even two functionalities, but just more functionalities to robots or also. And if we can use some of the robots to deliver us from one point to another one, why not also, as in the case of horses or cows, make them edible, so that we would kind of give a few functionalities of the animal to the robot. And that was actually an inspiration. That was a question that we asked us. Are we able of building such type of the robot that can be used not only for its straight needs like grasping something, sensing something, but also as a food, right? And that's what we did actually. So we built these actuator, and that was presented in 2017 on IRAS in Canada. So it's a soft pneumatic actuator. You already saw them today. Here we're applying different pressure in order to bend it as much as we can. That's what you see here. That's just one actuator. But then what we can do, we can actually take two of these actuators that can bend, and we can use them as a gripper to grasp different objects, as you see here with an apple, right? And we can grasp different objects, not only the apple, but also Lego, mandarins, eggs, different things. And here, what was the challenge actually for me? So probably this part can be more interesting to master students or bachelor students. So that's actually the moment when I came to the lab. My advisor has just an idea of what to do, but the material itself was not well developed, let's say. And the challenge he faced was that we would like to build a material that has mechanical properties same as silicones, but can be edible. And he did a great research on different components that can be used as the core part of the material and also as a plasticizer in the material. And out of this, you see, actually he collected the data from quite a lot of papers. And then out of that, we decided to develop this material based on gelatin, and that you see here as the main material, and glycerol as a plasticizer. And that was actually my part of work back to 2017. So what I did the whole semester, I was mixing the material in different proportions, different ratios of gelatin, glycerin, and water to get them the samples that looks like a sheet of material, so that I can, after that, laser cut them in a bone-like shape and then do tensile test of the material. And then by applying different hyperelastic material model, that could be Neo-Hookean model, that could be Yale model, we can get the final stress strain curve in order to compare the models that in order to compare the material that we made with the real silicone. And actually we succeeded at, and we built the material that mechanical properties are really close to commonly used silicone Ecoflex 030. And yeah, here I would like to share with you some insights of what I went through this semester project. So first of all is how to make an actuator, right? That's exactly what you saw already, right? So I just did different molds. And then what I tried to do, I tried to pour my material inside it, let the water, let it just solidify, and then take it out. And what I found out, actually, that was absolutely weird to me. That's actually what you see here on the left side. These are just different designs, how they look like. And then on the right side, you see how my design looked like after the water evaporated. And for me, that was absolutely non-understandable moment, right? Because I just saw the videos on YouTube how people develop the actuators made out of silicones, but there is nothing like that. The material doesn't shrink. just because that's silicone, right? There is no water, there's nothing to evaporate. But here, when you're developing the structure, you should also take into account this shrinkage of material. And that was actually the inside. That was an important step that we didn't take into account it at first. And then we had to design our molds in order to be able to forecast how the material would shrink, okay? So then in the end, we made this first edible actuator and gripper. And what is interesting, when it's already done, we're also looking at this device and we're trying to understand what are the, let's say, advantages of these material. And advantages were extremely interesting, actually. First of all, this material is biodegradable, right? Compared to silicone. Silicone is not biodegradable material, meaning that if, for example, for some purpose, we're going to use it in the nature, we can just throw it away and it would just degrade there. Or if then you would like to build a robot, let's say caterpillar-like robot that can just crawl inside our body and put, for example, some kind of a pills, medicine into a certain local point in our stomach and then degrade there, it's possible. And what is also very interesting that this material has self-healing capabilities, meaning that you can warm it up. If there is a hole, you can warm it up and then this material would self-heal itself. With silicone, that's extremely important, actually. That's absolutely impossible because silicone, it's thermoset. It's not a thermoplastic. And when we show this, the results of this project, that's actually the moment when the industry partners got interested in what we did. But it was not absolutely because of the research question that we asked. The question that, would it be possible or not to develop this first edible actuator? They don't care about it, but they do care that it's, for example, self-healing. And if they use this material for any purposes and there is a hole or it's damaged, they can repair it. They don't need to fabricate a new one and put it so that they can save money out of it. Or that it's biodegradable, meaning that it's more eco-friendly. And you know the trend in the world is now that we're more going for sustainable solutions to decrease our environmental footprint, right? So yeah, that's kind of the moment when finally academia meets industry. That's right on this stage. So yeah, now probably I would, let's say I would go also for a few more slides on another project that I was working on. So after that, when this project was done, I was also working on the stretchable sensors, soft sensors. And what is the motivation of it? That's actually what you see here on the left. It's an exosuit made by Harvard Biodesign Lab, led by Connor Walsh. An idea when you are building the exoskeletons should be people are actually trying to decrease the weight of the skeleton as much as possible, right? So all the components should have really low weight. And that's why they started building new sensors, for example, soft sensors that are first, they have the same mechanical impedance mismatch as you saw before as our skin, but also that are extremely lightweight, right? And we decided to go for a capacitive sensing instead of resistance sensing. That was probably more popular at that moment because the error is extremely low after multiple cycle tests, like 10,000 cycle tests. And also it works at a larger range of temperature, because if, for example, the temperature is extremely high, the resistance can be changed and it could cause some noises and problems with the, for example, determination of difference between two states, right? For example, the inextensible and elongated sensor. So, and also the sensors itself are first a little bit expensive. The component that people were using are quite expensive. For example, liquid metal, it's very, very expensive component actually. And we decided to go for extremely cheap components. It's Ecoflex 030, a very cheap silicone, and carbon black as a conductive part, extremely cheap too. And Ecoflex is also quite stretchy. we can stretch Ecoflex up to 500% of strain. That's quite a lot. Also, we would like to go for another fabrication method. We would like to propose a fabricated method that is that can be used potentially for batch manufacturing of different sizes or batches of sensors, right? And what we use, that's just, you can see it here on this slide. That's a layer by layer technique that you already actually met today when I was talking about the dielectric elastomer actuator with electroadhesion. So what we have here, we have a PT layer. Then on top of the PT layer, we just pour some liquid silicone. Then we plate cast it. So we make a really thin layer out of it. Then we put it in an oven. That's how we form the first layer with a thickness around 100 microns, okay? Then after that, we put on top of it a layer of conductive silicone, and then we put it in an oven. So here, the layer of the thickness of this layer is around 20 microns, so it's extremely thin layer. After that, we go to the laser cutter and we actually etch the surface. So we remove some of the conductive silicone. Let me show you how it looks like. Look at this picture here. What you see here, that's a structure composed of 3 layers. It's a silicone layer, conductive silicone layer, then we etched one of the electrodes with these V shape on the one end. And then we put one more silicone layer. So let me go back. So that's actually what I showed you. Step 4 is equal to this picture here, right? You have 3 layers. After that, we put one more silicone layer and etch the electrode, but now on the other side. And then we encapsulated everything in the silicone here. That's actually what you see here. That's a sensor that could be used to measure. It is actually a sensor with 2 modes. We have a resistive mode. So by connecting to these 2 cleans in the bottom and upper part, we can measure the resistance change. But by connecting to 2 cleans on one side, we can measure the capacitance change when we're stretching this sensor. And that actually was my second semester project. So my second semester project when I was a master student was to, first of all, fabricate these sensors and then do the whole characterization in terms of different things. So what was my part here? I had to link together the laptop together with LCR meter, that the device that we use to measure resistance and capacitance change, together with linear stage that you see here. Actually, that's a linear stage, this long thing here that could go back and forth, right? And a sensor that you see here is mounted right on the linear stage. So that out of that, we collected quite a lot of data. We collected the data on the repeatability. We took a look how the capacitance is changing, how the resistance is changing under different strains. And as you see here, what is interesting that here we have some kind of a hysteresis in the resistance measurement and almost no hysteresis in the capacitance change. So that was already advantage of capacitance measurement, right? Then if you will go and take a look, for example, on the strains under different times, you will see the response of the capacitance measurement approach is faster than the resistance approach. And also, if you will take a look at the change in the resistance and capacitance under different temperatures, it's much less in case of resistance change, in the capacitance change rather than the resistance change under different temperatures. And then in the end, finally, we built an example of an application. That's a smart glove. That's actually right here. You can see in my office still for 4 years. That's a smart glove where we can bend our fingers. And when we bend our fingers, the signal is changing, the capacitance is changing. And this glove can be used, for example, to control drone or any other purposes. Okay. So yeah, I think I will just skip it. And yeah, in the end, what I would like to tell you guys, I would like to tell a little bit about the work in the research and development sector, what I'm currently working on, right? Some people, or yeah, quite a lot of people I met, think that we are people from research are a little bit, weird guys that who doesn't really care about the I don't know salaries, etc. And not only I met these people not only in Russia but also in the US. There is this guy. His name is Doc Brown. Probably you saw him. He's a little bit, seems to be a little bit psycho, right? But honestly, I would say that it's not absolutely the case in the in nowadays. So and why it's not that, I don't know. In my opinion, probably that's because people in academia are also evolving, as well as their view on what's going on. And quite often, actually, people use academia, or people that are currently now in academia, that are doing academic projects, PhDs, just use it as the first step for their future ultimate goals. For example, every year, quite a lot of new startups are popping up, even in our lab or in the labs around us. Here are just a few examples. You already saw this drone today. That's just a spin. That's actually the startup from our lab. There are a few more companies that are built also on the research works, like SenseFly, Flyability, and there is also the thing called WIS Institute. WIS Institute, usually that's a organization inside the university. It exists, for example, at Harvard or at ETH Zurich. These are actually the labs that are trying to develop as much more startups out of their academic project as possible. So the main goal of these guys is actually to build startups out of their academic input right after. So yeah, I think I would stop here. So here are my contacts. Thanks a lot for your attention. If you have any questions, I would be more than happy to answer. Yeah.
Thank you, Yegor, for the amazing, inspiring lecture. I really enjoyed it. Well, we have some questions in the chat. I will tell you.
Yeah, sure. Absolutely. Let's go.
Here we have the first question that says, if we wanted to create these robots, what kind of materials is it recommended to use? For example, I think this question is more about for the aerial robots.
For what robots? Edible or aerial?
Aerial.
For aerial robots.
Yeah.
Depends also on the robot you would like to build, right? So if what type of drone is it? Is it a winged drone or is it a quadricopter? What I know, in our lab, we're using a lot of composites, carbon fiber. We use a lot of carbon fiber. So yeah, these are just kind of a basic material that we use to build them. With, for example, with, for example, winged drones, we use quite a lot of foam, actually. Foam. So you need something that has a really good ratio in terms of the stiffness to the weight. So we would like to find something that is able to at least bend a little bit as a foam, but be extremely lightweight, right?
Okay. The other question is more for exoskeletons. It says, like, what are the challenges of using elastic elements or soft robotics in exoskeletons?
Mm-hmm. I would say with so you see, exoskeleton is extremely complicated, large structure. I'm not an expert in exoskeletons, but what I know so far, in exoskeletons, you could probably have a lot of different things. You need sensors, you need actuators. Probably, anyway, the most largest part would be your batteries, right? Because if you would like to have something that can work autonomously, right, you would need to have these batteries on board, meaning that on you, right? Then about the soft elements, definitely soft elements as sensors make sense to me. Soft elements as, for example, actuators to develop motions that's much more complicated to do actually, because if we would like, for example, to integrate soft pneumatic actuators, you would need also to have a compressor. That's this large thing on you, right? Probably that would be not the best solution, right? But on the other hand, you can use just electric motors, right? That are probably much better in terms of the mechanical output. However, they are rigid, right? So I would say that for now, exoskeleton, it should be some kind of a mix between rigid components and soft components, with, of course, future focus in more on soft components in it.
Soft components. I think that answered the question. Well, this is on the same topic. Just in case that, for example, some of our students wanted to focus his projects on exoskeletons, what would you recommend to that project, to that student, for making a prototype or a prosthesis, for example, using soft elements or soft materials?
I see. So I would say that in order to advise you on that, first of all, I need to see the literature review, right, of the field. So I'm not that familiar with the literature review of what's going on currently in the exoskeleton domain. But what I definitely know, what you saw, guys, today, there are definitely already currently existing soft sensors that could be applied onto the human body, right? What's going on with the actuation part, that's much more complicated. I personally remember there was a work where guys tried to do a spherical joint that actually is a soft pneumatic actuator made by Connor Walsh Lab. And they showed it to Bill Gates actually a few years ago. I just remember he passed by their lab at Harvard. But if you really would like to get more insights about the exoskeletons at EPFL, there are special labs that are focusing on that. So you can just contact me after. I will just give you contacts so that you can go through their papers and what these guys are working on. These guys are really more, I would say, application-driven guys. So they really would like to develop a device that would help people. See,
Yeah, excellent, George. Thank you. The other question is about the soft gripper that we are seeing on the screen. It says like, what are the difference on characteristics of your edible soft gripper versus the silicone one?
Yeah, that's a good question. So I would say that in terms of the mechanical performance, we would like to be exactly at the same range. So we would like to use the edible materials that have not exactly, but really close mechanical characteristics as the regular one that we use in soft robotics, like silicones or acrylics. Why? Just because we know their behavior. We don't really know it for every particular case, but for quite a lot of them, we can already model them. And that's actually the complicated parts about soft robotics. In soft robotics, you're always faced with non-linearities. Every time you're faced with non-linearities, it's complicated, right? Because you need to do something with it. You need to model it somehow. You need to predict it somehow. It's not that easy. And that's the reason why we're not looking for the materials that have different behaviors. Because in this case, we would need to go through all this way one more time, right, in order to develop new models for them, etc. So in terms of the mechanical performance, we would like to be exactly in the same range as we are with silicones or acrylics, for example. But what is the difference between them? That's their nature, that these materials are edible, right? But edible probably here, it's more like advertisement word. I won't really, count on that much. I would say that we would like to have something that is biodegradable, that is eco-friendly for our environment. Let's imagine that, for example, in the future, in the lake that we have here in front of the campus, there are some soft robotics fishes made out of, for example, silicone. If this fish made purely out of silicone will die, and then it will just it would get stuck on the bottom of the lake, it would never degrade because it's made out of silicone. But if it's a, let's say, eco-friendly fish made out of edible or degradable materials, we can easily leave them there, right? I know that probably you know this problem of ecology is not that close in every university in the world due to different reasons and, let's say, the direction of the countries. But here that's a big problem, right? And that's definitely something that we would like to focus on as much as we can. And yeah, apart from that, as I mentioned already, what is great about some biodegradable materials, that these materials are not thermosets. They are thermoplastics, kind of, meaning that we can also have self-healing capabilities, and self-healing capabilities quite often is equal to saving money to industry. And industry, these guys love to save money, right? That's the reason.
Okay, which other application do you see using this kind of material? For example, you present a soft gripper, right?
Yes.
It could be, well, we could use that material or that technology in some kind of manipulator or some kind of robot system, for example. And which one do you think?
Yeah, I would say that this was just the first step to kind of show you that this material itself is compatible with the material that we currently use in the soft robotics and can be used for the common users. For example, be used in the development of actuators and sensors. But that's just the very first milestone. In my opinion, in the future, we can use these materials, first of all, to build the robots that can deliver different medical pills or any medical things locally inside the human body, for example, to the certain position of the stomach. Then for example, that's gonna be a mix of a few actuators, looks like a caterpillar that can climb into your body, go down, come to the certain position, and then just degrade there, right? That's the first thing. The second thing that could be used, for example, to deliver food to animals, right? Let's imagine that you have the same kind of a caterpillar robot, and if some animals are dying, you can put pills inside these robots, and these robots would just go through the jungles, and the animals would just eat them together with the pills inside. So I would say that definitely it could be used in the medical domain.
Yeah. Amazing, just amazing. And another question that it says, how did you deal with the evaporation in your model? Evaporation of the water.
Yeah, absolutely great question. I would say we did not build a mathematical model to predict it, because the material itself is novel, meaning that we don't have any constants of this material, right? We just know some mechanical properties that we got out of 3-point flexural test. And that's actually the super challenging part of soft robotics. Sometimes when you're trying to model something, you have to know some information about the components you're working with. But in soft robotics, quite often we're working with absolutely novel materials, so we don't even have the numbers to put in the model. You see the problem? And actually, that's why that's more, I would say, empirical approach. So we just built 10 different molds with different parameters. Then we just pour material in all of them. We let it evaporate and just found out the most closest one. That's it.
That's it. Just experiments.
Yes. Mostly we're using experiments. That's actually our approach. We're always trying to rush the first prototype of the device as soon as possible with only rough calculations, rough modeling that not gonna take weeks of working. Usually it just takes 5-10 hours of modeling just to roughly estimate orders of magnitude. Because in soft robotics, when you're dealing with a lot of non-linearities, you cannot really predict what's going to be in the end. And that's why you just need to have actually the skill of rapid prototyping. That's the most essential skill that you can have in this field.
And did you plan to obtain some mathematical model for this kind of gripper?
There are already quite a lot. For the soft pneumatic actuator, that's a really well-known field. There are quite a lot of them. For this particular one, there is no sense actually doing it because the mechanical properties are as close to silicone, meaning that we can just apply any already existing silicone modeling approaches that are already existing. So yeah, let's say for this particular device, it's more or less done. Yeah.
Okay, thank you, Igor. Here we have another question. It says, have you tried to 3D print the soft gripper with flexible materials? If yes, what were the results?
Yeah, absolutely great question. So first of all, I haven't yet. There are definitely printers that can do that for us. In our lab for now, we're only printing NinjaFlex. NinjaFlex, it's a soft stretchy polymer that can be used, for example, to build different tensegrity structures. But we never tried to print the edible material. But what I know, actually, there was a paper, I think. I'm not sure that it's already popped up, but there is a paper when people are printing with hydrogels. Definitely, there are quite a lot of them. And there should be a paper when people are trying to print with gelatin glycerin mixture, exactly the same mixture that we're used in this project. Gelatin glycerin mixture, actually. Yeah, I've never tried, but I would love to. I would love to try. I think that's super exciting.
Yeah, will be amazing to print this kind of gripper, right?
Yeah, that's true. That's true.
What will be the challenges? What do you think?
Well, the challenges would be how to uncure layer on another layer, right? First of all,
yeah,
because in the 3D printing, usually it is layer by layer technology. In the end, right? You're doing it layer, 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 layer. How to do it here? Would this material uncure on each other? Would it be homogeneous after that or non-homogeneous? How to always keep it? How to trigger the solidification process, right? How to deal with evaporation. So yeah, extremely lot of challenges, I would say.
Yeah. Moving forward to aerial robotics, we have a question about that topic. It says, relates to delivery drones. What is the mesh for? Is a
to protect.
You say, what is the max weights?
Okay, I see. So the first question, why do we need this mesh? That's to protect the propellers and the pellet with your goods inside, right? So the mesh is to protect the propellers first, or to protect people from the propellers, so that the propellers won't catch your fingers when you're trying to grasp the drone. Then the second thing, it's about the packaging. So I think you can find this video on YouTube. This drone was already used, I think, in Africa to deliver medicine, different medical things like pills to people that are living in really cluttered environment, dorms, far from the cities. And for example, for about the max weight, I don't know. You should check the paper. Yeah, don't know this information.
Just you show us the bird-like drone, right? With
Elytra. Yeah, sure.
Yeah. With what kind of controller did you use there? Because you have a dynamic winds, right?
Yeah. I see. Oh, I have no clue. I have no clue. That's absolutely not my field. I think I left their link. If not, contact me after. I will send you. This is quite new actually work done by our lab. So yeah, you can check it out there. Otherwise, you can always contact my collaborators who've been working on that. They will provide you all the information.
Perfect.
Okay, I have a question, please, Jose.
Sure.
Go forward.
Okay. Hi, Yegor. Well, my name is Job Ledesma. I am the head of the Mechatronics department here at the Bolivian Catholic University. So glad to meet you, and thanks for your speaking, for your talk.
Always welcome.
And one of my questions is related to this. If this soft gripper, for example, is already commercially available to us to buy this kind of things, or if you already have a research about the combination of materials in some point that we can reproduce your work, maybe, or the work of your center.
Sure, absolutely. So first of all, this work our lab has a patent on it, right? This work is not commercialized yet, but you, of course, easily can reproduce it. You can just download this paper that was published on IROS a few years ago. There is a recipe. You can just follow this recipe and try to build it using the same fabrication approach that we were using here, and use it for I think academia, etc. Everything that is related to commercialization, that's definitely not to, because I'm doing research here. I'm not commercializing anything. But if you would have this interest of commercializing, I think for this purpose you would just need to contact my boss, the head of the Laboratory of Intelligent Systems, Dario Floriana, and discuss it with him.
Do you have some experience about the application of your soft grippers, for example, in industrial applications? Did you design some of these new kind of grippers for the industrial applications?
I personally never been working with the industrial partners that would like to get some soft grippers. But if you will open for example, US market. In the US, there are quite a lot of companies that are only working on soft grippers based off soft magnetic actuators that look exactly as I showed you today. For example, they use the grippers to grasp different fruits and veggies in their centers. For example, to move the veggies, etc. So I would say that in the US, that's already commercialized, and probably for like 10 years or so. But here, I've never been working with any commercial partners on that.
Okay, thank you. And the last question is related to how did you implement the algorithms for this kind of soft robotics, for example, because due to this high flexibility and these other kind of non-linearities that you have, which kind of algorithms did you usually implement in this kind of soft robotics?
Mm-hmm. Well, what do you mean by algorithms? Algorithms,
like
what
Ph.D, like robust control, like predictive controls.
I see. So actually, in my research, I'm not working with the algorithms and control at all. So my research is always focusing on developing new devices. It could be rather the actuators or sensors or variable stiffness technologies. But the control part, that's usually done. We quite often we don't even work on the control for some of the works, just because it's not the core challenge there. but even if we're working on the control, that's just not done by me. That's just done by collaborators or engineers that are more specialized on the control. So yeah, I cannot really comment a lot here because I'm not really working on that much. Yeah.
Okay, thank you very much, Igor. Thanks.
Yeah, thanks a lot for your questions. Yeah, it was a pleasure.
Thank you, Igor. I don't know if some of our participants in the audience have any questions. Please. Well, I will check the chat if we have any other questions about this one related to. Okay. One more question, Igor. I think.
Yeah, sure.
We will the last one. For young university and young people that want to introduce himself or ourselves into academia, into researchers, what kind of advice could you give us to doing great researchers in academia and then link them to industry, for example, or just in academia?
Okay. So that's actually a complicated question. There is no that just I cannot just give you a simple advice because that's a really complicated topic. I think that's can be even the topic of the independent lecture in some sense. I would say that in industry, in my personal opinion, research is the most interesting part of work that you can do. If you would like, if you would like to work in the research field because it's interesting, you have to have high level of education. Usually, if you will open the positions in the US, any R&D positions require PhD in the field. Okay, so I would say that if you would like to go for a R&D position in a good company, you have to start with a PhD, right? Now, in order to just be admitted to the good program in the good university, high-ranking university, you should have a few things as the undergrad or master student. You should definitely have high GPA, high grade. So your average grade should be high. That's the first thing. The second thing, you should have some experience in the research that you gain during your semester projects or your bachelor final projects, master's project. And it would be always better to have some publications as the co-author in the good papers, or in the good journals, or in the good conferences, right? That's the second thing. The third thing now is that the competition to get this good position in the top labs around the world, that's quite challenging. That's why, in addition to high grades and expertise, some experience, you should also have some good soft skills, meaning that you should have a decent level of English, and you should also be able of showing your results in a proper way, meaning that you should be good at storytelling. And this is actually important part. Some of the people are lacking it, but that's actually something that professors are asking for now. Okay, and then there is a new trend that I just, in my opinion, pop up not that much time ago. Is just that professors are looking for people with the US experience. I would say with at least a projects, some semesters project, master's project, exchange semesters in the US university. Why? Because the fact that you survived in the US means that you first of all have a decent level of English, and that probably you gained some skills in terms of storytelling and presenting your results to the general public, because US people as well as people from Canada are really, really good at these things. I would say that it's just my personal opinion, and probably I'm wrong here, but in my opinion, if you have such type of experience, it would be definitely a good point to your CV.
Perfect, excellent. Thank you, Igor. Thank you for being here, for
Yeah,
you
sure.
for the amazing lecture. We would love to, in the future, if possible, to collaborate in other things.
Yeah, sure. I mean, I was happy to discuss with you guys. So yeah.
Perfect. Well, again, thank you.
Yeah.
Thank you. I don't know if any question or something. If not, we will end this talk here. And again,
Okay.
and again.
May I just take a picture of all of you guys, okay, for my parents? Okay, thanks a lot. For me, that was a pleasure also. Thanks a lot for listening. Yeah, we'll be happy to discuss anything that you would like to discuss, or also meet you guys in the future. Yeah, thanks a lot.
Thanks. Send the picture to Pardikov.
Exactly. To our former advisor, right?
Yeah.
Absolutely.
Something to say?
No, on behalf of the Mechatronics department here, we already appreciate your presentation, Yegor. Thank you very much, and maybe we will see you in another opportunity. Thanks.
Sure, absolutely. Yeah, thanks a lot.